Okay, welcome to Introduction to ML CS 97 NPTEL initiative. So I am Moinak Biswas. I'm a second year PhD student at Brain and AI department in IISc Bangalore. So today we'll have an introduction to this course. So I'll be taking tutorials on the Introduction to Machine Learning course taught by faculty of IIT Kharagpur, Professor Dr. Sudeshna Sarkar. So today we'll do two questions. These will be relevant to students of class 11 who will be learning functions, and also people who are learning linear algebra in the UG courses. So let's take this example where f of x is equal to x plus 1 over x. So what happens is we are told to find the maxima and the minima of this function. So first of all, for these type of questions, we need to understand what is the range, what is the domain, and what is the codomain. So if nothing is given, it is considered that the function f mapping from x to y is a R to YR mapping. So this is a domain and this is your codomain. And we all know that the range is a subset of the codomain, which values the function can take. So we can clearly see that this function takes value in R. That means minus infinity to infinity, and we leave out 0 because the limit does not exist at 0. So you can clearly see limit x tends to 0 plus x plus 1 over x is positive infinity, and limit x tends to 0 minus x plus 1 over x is negative infinity. So left hand limit is not equal to right hand limit. So function is not continuous at x is equal to 0, and limit also does not exist. Which is obvious because function, this is both of these will be going to infinity. So what happens is, so at 0 the function is not defined. So and what is the range of the function? The range of the function we can easily see by seeing the value where this function attains a local minima or a local maxima. So what is the shape of the function? We have seen at infinity, at 0 this function is infinity, positive infinity, and at minus 0 this is negative infinity. So you can see one thing from here, that this function will actually give you this function will be decreasing in some way, because at limit x tends to infinity, x plus 1 over x is infinity again, and limit x tends to minus infinity, x plus 1 over x is equal to minus infinity, because after a certain point 1 over x decays to 0, and f of x can be approximately said to be x. So after a certain point we can expect a linear sort of a characteristics of this function, both increasing and decreasing to infinity. So now we'll have to see the extremas of the function which are not at the endpoints. So what we can do is we can take the derivative, as we have seen, of this function. So we get 1 minus 1 over x square. Derivative of x is 1, and you can just use basics of derivatives and you set it to 0, and you will get x is equal to plus minus 1. At x equal to plus minus 1 you have extremas. So you put the values of f of 1 is equal to 1 plus 1 by 1, that is 2, and f of minus 1 is equal to minus 1 minus 1, that is equal to minus 2. Okay, so at 1 you are seeing the value is equal to 2, so it goes down here and then it increases like this, and again at minus 1 this is going up to 2 minus 2, and this is again going to infinity. So the curve will be like this. You can check this on any software. So this should be somewhat like this using the basics of calculus. Okay, now one can say that the infinity is the maximum value that the function can achieve, and the minima and the maxima is plus infinity and minus infinity. 0 if the function is not defined, so we're not going to consider that. But so the range we can first write it down as, it's from minus infinity, that's an open set because we're not considering the real numbers not contain infinity. So minus infinity to minus 2, we can see here minus infinity to minus 2 is in the lower graph, union 2 to infinity, that is in the top part of the curve. So this is the region, this is the range of this function. So this function, again infinity is not included, so infinity does not belong to the range of the set because we're considering only real numbers. Therefore this is not a maxima or a minima. So this function has only two local minima and maxima. Global maxima, global minima does not exist. So we can clearly see from the graph. We can also take the second derivative. It will be very easy, second derivative test, if it is greater than 0. So you can see that f double dash x is nothing but is equal to 2 by x cube. So you can clearly see from this equation. So this is 2 by x cube. So given x greater than 0, f double dash x is positive and f double dash x is less than 0 if x less than 0. Means that for x equal to 1 you have a minima and x equal to minus 1 you have a maxima. That's what you're seeing. So x equal to minus 1 you have a local maxima, and x equal to 1 you have a local minima. There is no global minima or maxima. The second question we'll be doing today is related to the linear algebra part. So we'll be seeing, the question was given that you have to find the product of eigenvalues for this matrix and the sum of eigenvalues for this matrix. So instead of doing this simple finding out eigenvalues, that's a very trivial exercise, you can try it on your own. So what we'll do is we'll prove an interesting case. So we'll try to prove something with the characteristics equation of this matrix, a general matrix, to give you ideas about what is the product of eigenvalues and what is the sum of eigenvalues. So let us consider a general matrix like this. So what is the definition of an eigenvalue? Eigenvalue or eigenvector is of such a vector that when you multiply that vector with a matrix, so the direction of the vector remains unaffected and it is actually scaled. So if you have a matrix, you take a linear combination in the column space. So what you happen is, so you have this some columns c1, c2 dot 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 cn, and you have lambda 1 dot 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 lambda n. So lambda 1 c1, so, or rather than I equal lambda I ci, I equal to 1 to n, it's only for a square matrix, is equal to, so let's put alpha here. So alpha I ci is sum, and we name this as alpha matrix, is sum lambda into alpha. So this is the equation. So you have this vector, you operate this with the matrix A, so it, after you operate that, it remains in the same direction, so factored by lambda. So that's what you've written. So A times lambda, you get some scalar lambda into the vector again. So this is the eigenvalue equation. That's a basic thing we all know about. So you take lambda this side and you set this to 0. So what happens is, this you get is, you have, this is from this equation, you can clearly see that this equation must have a null space, because you are seeing that x not equal to 0. If there is a solution of x not equal to 0 of this equation, that means this matrix A minus lambda I must have a null space. We can see, you can revisit your basics of linear algebra to understand what's a null space. In case you have a null space, so what happens is the determinant of this matrix is 0. So that's what we'll set it to. So you put determinant of this to 0 and you take the determinant of this matrix, so you get a simple quadratic. So what does this quadratic say? It's lambda square minus a11 plus a22 lambda. Simple, you just manipulate, so you get a11 minus lambda, a22 minus lambda, minus a21 into a12. So, and you set it to 0. So you get, this is known as the characteristics equation of a matrix. So you can clearly see the roots. Lambda 1 plus lambda 2 are the roots of the equation. From the basics of quadratic equations is nothing but a11 plus a22, that is equal to trace of a. And you can see lambda 1, lambda 2 product of matrix basic quadratic equations again is a11 a22 minus a12 a21, that is nothing but equal to determinant of a. So we'll use an inductive hypothesis to show that the trace is always the sum of the eigenvalues and the determinant is always the equal to the product of the eigenvalues. So you extend this, we have already got this, we have already got the determinant of this matrix. So what we do is, with respect to this row, you extend this determinant to compute it. So I'm just doing it with this, and the rest I am writing as some function of lambda. So if you do that, so you expand this equation, so you can see after multiplying by -1, so you can do some basics of this calculation. So to first concentrate on this term. So what do you see? So once you multiply this out, you see this, the lambda square term has two things. You have one here and you have one here. So you're going to add these two and you see again the trace coming up. So in case of a polynomial, the sum of the roots is given by the coefficient of the second power. We all know that. That's simple polynomials rule. So nth order polynomial n-1 gives you the sum of the coefficient of n-1 will give you the sum of the roots into minus. Of course, you multiply that with minus. We all know that's a basic polynomial. So you can clearly see that the lambda 1 plus lambda 2 plus lambda 3 is equal to a11 plus a22 plus a33. So this is again trace of a, or trace a3 you can say, because you're taking a, this is, you can write this as a3. So trace of a3. Similarly, you, without leaving lambda, you will get a non-lambda term. This is non-lambda term when you expand. You can clearly see, because you have a minus here, so with leaving out that minus, if you expand this, you will always have a non-lambda term that is always equal to the, when you expand, that is equal to the determinant of this matrix. You can work this out. This is a very simple exercise. So you will get the determinant of A. This is not at all complicated, because as a subtraction, you will also have a non-lambda term in that, and that will give you the determinant of A. So in that case, it will be a negative sign. So you will get, you can already see here one term in that. So that is with this. So if you multiply by negative, so it's negative. So you will get a term in terms of the negatives, and that is also, that becomes positive. So this is negative, this is negative, this is positive, and this is negative. So you will have, you will negate this. So your basics polynomials. So you first term, the sum of roots. So sum of roots, sum of lambda I is equal to, so if you have, we all know, so if a function, so if a polynomial p of lambda is nothing, is equal to lambda to the power n plus a n minus 1 lambda n minus lambda to the power n minus 1 plus a n minus 2 lambda to the power n minus 2 dot 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 a. So you have a0. So what do we know? That the sum of the roots, sum of roots of lambda, sum of the roots of lambda, that is equal to, so what do you have is, you get a negative an minus 1. And for this a0, you can see you have alternative positives and negatives. So this is positive, this will be negative, this is negative, this is positive, and so on. So they have n terms. So the product of the roots is given by a0, and you will have a minus 1 to the power of n. So you can clearly see why. If it was 2, you got a1, this is positive, lambda 1 lambda 2 was nothing but the product of the roots was equal to this term. So a, b, c, the third term. And in the case of the third one, you will have a negative sign. So it's minus 1 to the odd power, that the roots will be negative, and when they have an even power, the root product of the roots will be positive. So you can clearly see that the product of the eigenvalues give you the determinant of the matrix, and the roots of the eigenvalue, the sum of the trace gives you the sum of the eigenvalues. So this trace, so we can clearly write it down as 4 as the sum of the eigenvalues, and the product of the eigenvalues will be nothing but minus 2. I'm just expanding, I'm taking the determinant of the matrix. So it's 5 minus 4. I did it across this, and then about minus 4. So minus 4 into minus, so plus 4, minus 10, minus 8. So so you get this and this, minus 10 and minus 8, plus 2 into minus 4, minus 4. So you get this as minus 2, minus 72, and minus 16, that is equal to minus 90. So this is, we have seen the proof that the sum of the eigenvalues is nothing but the trace of a matrix. So we have seen you can generalize it to any power. So I just showed you up to 3. So sum of eigenvalues is equal to trace of matrix and product of eigenvalues is equal to determinant of the matrix. So that's it for today. We'll be meeting on Fridays from 7 to 8 for when we'll be starting off with the lectures. We'll be starting off the tutorials pertaining to the weeks from 29th. So that we'll be starting off with the tutorials related to the weeks in each in the course. So we'll be starting off the basics, and we'll be going up, solving equations, and we'll also do some programming assignments to familiarize with you with the machine learning framework and also the theory of it. And problem solving will also be done. So thank you for today. Bye.